Hello, everyone. My name is Yu Guo. I'm from Midwestern State University. Today, I would like to bring to you my presentation on period 3 motions in a periodically forced spring pendulum. In this presentation, we'll first talk about introduction, and then we'll describe the methodology that we use, and then we'll talk about discrete mapping and how it can be used to describe different periodic motions. Then we'll demonstrate some prediction and simulation results. Finally, we'll conclude. So pendulum is a very simply constructed system, yet it possesses complicated dynamical behaviors. So many researchers has been doing research on it, investigating the dynamic behavior of such a system using perturbation method. In order to obtain analytical predictions, in 2015, Law developed the discrete mapping dynamics to predict periodic motions in nonlinear dynamical systems, and such method has been successfully applied to systems like Duffing oscillators to obtain very good results. Thus, the same method is going to be applied to a periodically driven spring pendulum in this presentation. First, let's go over some theory. If we consider a nonlinear dynamical system, and the system is described by a vector function in a continuous nonlinear vector space, then if such a dynamical system has a periodic motion and the period is 2 pi over omega, then we can always find a set of discretized time vector tk with the corresponding discretized points xk that is very close to the original orbit of the periodic motion. Similarly, with the same system, if we consider a period m motion with its period equal to m times t, where t is 2 pi over omega, then we will be able to find a set of discretized time vector tk with a corresponding set of points xkm, that these discretized points are very close to the original orbit, and thus can be used to represent the original orbit. So with such an idea, a mapping structure can be constructed for a period m motions, as shown in this equation, with mapping action from Pmn all the way to P1. And the Jacobian matrix for each of the mapping can be calculated as the change of ending point corresponding to the change of initial point for each of the mapping. Then the total Jacobian matrix of such a mapping structure can be calculated by multiplying the Jacobian matrix together following the mapping action order. The eigenvalues can be evaluated for such a Jacobian matrix so that we can evaluate stability and bifurcation conditions. So let's look at a periodically forced spring pendulum. The pendulum system is shown in this figure, and the equation of motion is shown in these two equations. We can rewrite these differential equations into a state space form. And a discretized mapping can be defined for such a system so that one mapping maps from x1k minus 1, y1k minus 1, x2k minus 1, y2k minus 1 to x1k, y1k, x2k, y2k. Each of the mapping will follow this structure, and the governing equation of the mapping can be described in this form. And for period 1 motion, then we can use a mapping structure that starts from Pn, mapping action all the way to P1 to describe such a periodic motion. The special point here is that the initial point x0 is going to equal to the last point xn, so that the periodic condition hold. And then following the methodology we described previously, we can calculate the total Jacobian matrix based on the Jacobian matrix of each of the mapping, and then evaluate the eigenvalue. In such a system for a Springer pendulum, we have 4 different eigenvalues, and if all eigenvalues has a magnitude less than 1, then the periodic motion is stable. If any of the eigenvalue has a magnitude greater than 1, then the periodic motion is unstable. If one of the eigenvalue equal to 1 and the rest of the eigenvalue has a magnitude less than 1, then this is saddle node bifurcation. If one of the eigenvalue equal to -1 and the rest of the eigenvalue less than 1, then this is period doubling bifurcation. If a pair of the eigenvalue are complex conjugates and their magnitude equal to 1, and the rest of the eigenvalue has a magnitude less than 1, then this is a Naimark bifurcation. Now let's look at some predicted bifurcation trees for periodic motions. So this is a period 3 motions bifurcation tree. As you can see, this bifurcation tree is quite complicated. We have some symmetric, symmetric periodic motions, and we also have some asymmetric periodic motions in here. On the left-hand side here, we're showing the periodic node displacement for the pendulum, and on the left-hand side here, we're showing the periodic node velocity for the pendulum. When you see a solid line, when you see a solid curve, that means this motion is stable, and when for an unstable motion, we're using dashed lines to represent those. When a pair of asymmetric motion appears, the asymmetric pair is shown by different color using black and red. So whenever you see a pair of black and red color, they are representing a pair of coexisting asymmetric motions. You can see here we start with a symmetric period 3 motion. At the left-hand side here, we encounter a saddle node bifurcation with jumping phenomenon, which connect to unstable motions. And then as the stable period 3 motion go to the right, here we encounter another saddle node bifurcation, where it gives us a pair of asymmetric period 3 motions, and then we have period doubling bifurcation introducing period 6 motions, and so on. The symmetric period 3 motion will go stable, unstable, switching from stable, unstable a couple times as the excitation amplitude increase, and the unstable motions encounter unstable saddle node bifurcations where they are associated with jumping phenomena, and we'll zoom in and show you later on. So this is a zoom in for the previous bifurcation tree. The range is from 12 to 15, and here you can clearly see the symmetric period 3 motion with jumping phenomenon on its left, and with a saddle node bifurcation introducing a pair of asymmetric period 3, and then period doubling bifurcation introducing a pair of asymmetric period 6, and then a another period doubling bifurcation further introducing further period 12, period 24 motions, something like those. But here we're not showing those on this graph because of the very tiny stable range. Now here is another zoom in of another section of the same bifurcation tree. The range is from 17 to 23. In here, you can see another branch of asymmetric motions. This asymmetric motion is introduced by a saddle node bifurcation at this point right here. This saddle node bifurcation is from the same symmetric period 3 motions, and you can see the asymmetric pair period 3 motion are introduced, and it encounters twice a 2 branch of period 6 motions. You see here, the first one is right here, the period 6 motion introduced by a period doubling bifurcation, and it ends at another period doubling bifurcation. For the whole range, the period 6 motion is stable, so we don't see any further period doubling bifurcation. However, for the second one here, you see we have period doubling bifurcation here, and then another period doubling bifurcation for the period 6 motion, and then you will see more as it goes, with the stable range shrinking exponentially. Now let's look at some simulations. This is a symmetric period 3 motion that is taken at the excitation amplitude equal to 13, which is at this range, in this range. So the symmetric periodic motion here we show is on the left hand side. Here is the phase, is the trajectory for the pendulum motion, and on the right hand side is the trajectory of the spring motion. You can see that the the trajectory of the pendulum motion is basically symmetric to itself according to the point pi 0, this point. The green dots are representing the initial condition and the periodic nodes. So all the periodic nodes are denoted by 1t, 2t, and 3t. And because this is a period 3 motion, the last periodic node 3t should match up with the initial condition. And after a period doubling of the after a saddle node bifurcation of the symmetric period 3 motion, a pair of asymmetric period 3 motion will be introduced. Here we pick an example at the Q0 equal to 13.5, and here what you see is a pair of asymmetric period 3 motion. On the left hand side here, on the top left here, we're showing the black branch, and on the top right here, we're showing the red branch. The two branches coexisting at the same time, and they are symmetric to each other. You can see that their trajectory are symmetric to each other, according to the point pi 0. Now, for both branch, the motion of the spring is the same. So if you look at the trajectory of the motion of the spring, it's basically the same for both branch. And on the bottom left here, we're showing you the displacement of the spring. With the green dot representing the periodic node of the black branch, with the red dot representing the periodic node of the red branch. You will see here, for the periodic node of the black branch and the red branch, there are always a phase difference of 1/2 pi. Finally, after period doubling for the period 3 motion, a pair of asymmetric period 6 motion will be introduced. And what you see here, on the left-hand side here, we're showing the period 6 motion of the black branch, and on the right-hand side here, we're showing the red branch. Again, because they're asymmetric pair, they are symmetric to each other according to the point pi 0 in the phase plane. And similar to the previous motion, the motion of spring are the same for both black and the red branch, which is shown in here. The trajectory of the spring is shown in here, and the motion, the displacement of the spring motion is shown on the bottom left here, and you will see the green dot representing the periodic node for the black branch, and the red dot representing again the periodic node for the red branch. And once again, if you look carefully, you'll see that here between the periodic node of a black branch and the red branch, there is always a phase difference of pi/2. As a conclusion, the dynamics of a periodically forced spring pendulum was investigated in this presentation. We talk about discrete mapping structures, how discrete maps can be defined, and how mapping structure can be used to represent the different periodic motions. We presented the analytically predicted bifurcation trees for period 3 motions, and we illustrated a set of simulations demonstrating the change from symmetric period 3 motion all the way to a pair of asymmetric period 6 motions. Thank you.